All right, acids and bases, moving on. We're going to talk about reactions of acids and bases with water, definition of Bronsted-Lowry acids and bases, and then talk about what it means to have a conjugate acid-base pair. All right, so question to keep in mind as we go through this screencast, what are some other ways that we can define acids and bases? The traditional method and the most narrow is to define acids as being something that generates H plus in solution. Bases generate hydroxide in solution. Okay, that's the traditional, most narrow way to define it. Now we're going to go into a little bit more broader definition, the Bronsted-Lowry. Bronsted-Lowry acid is a molecule or ion that is a hydrogen ion donor. Now, hydrogen ion, and you should write these definitions down along with this short explanation. Hydrogen ion is an H+. If you remember, hydrogens have one electron, one proton. If I take away that electron, all that's really left is that nucleus, one proton. So we can call it a hydrogen ion, or a lot of times chemists just refer to that as a proton. So the more classic definition of Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a hydrogen ion or proton acceptor. So the acid gives it up and the base takes it. Okay. Now, conjugate acid and conjugate base, I think the definitions are a little confusing. When we see the explanation, it should clear it up. So a conjugate acid is the particle that forms when a base accepts a hydrogen ion. And a conjugate base is the particle that forms when an acid donates a hydrogen ion or a proton. Okay, for example, I have phosphoric acid, H3PO4, and water. Oops. Okay. If I look at this example, this is giving one hydrogen to that water molecule. Okay? That water molecule becomes this H3O+, and this phosphoric acid loses one proton to become H2PO4. Okay. Since this donates that hydrogen ion, it is a proton donor, it is the acid. The water is accepting that proton, it is the base. Now, if we look at the two products, I have the particle that accepted that proton, and I have the particle after that proton was donated. Okay. This, the one missing, like the proton or the H+, it is what is known, having troubles today, what is known as the conjugate base. And then that H3O+, that hydronium ion, is what is known as the conjugate acid. This is a base conjugate acid pair. This is an acid conjugate base pair. Okay, so they go together. If you notice, the only thing different between these is that H. The hydronium has one more H than the base that it started from. This conjugate base, H2PO4 negative, has one less hydrogen than the acid it comes from. Okay, and with neutralizations, you should be able to identify the conjugate acid-base pair. Okay, so let's look at another example. Okay, I have ammonia and water. Take a minute, make sure that you can predict the products. What is this going to do when I mix them? Come on, pause it. Predict the products. Hopefully, you could see that this NH3 is going to go to that ammonium ion. That H has to come from the water. So the water ends up being just the hydroxide, one hydrogen less. So on the reactant side, what is donating the hydrogen, or what is being that proton donor? Hopefully you can see that the water is being the proton donor, so it is the acid. The ammonia is accepting that proton, so it is the base. What does this base look like when it accepts that proton? Oh, it looks like NH4+, so this must be its conjugate acid. And that makes the hydroxide here the conjugate base. So these are a pair, and the ammonia and the ammonium are the pair, conjugate acid-base pair. So things to remember, hydrogen ion is commonly referred to as that proton, that's what's being transferred. Okay. The thing also to remember is that this really does not exist by itself in solution. It really is going to attach to a water to become a hydronium ion, but it is the particle that is transferred from that acid to the water, is that proton. Okay? And then you have the hydroxide ion as well. Okay. Now if we look at the two reactions that we were looking at, we have water here and we have water here. And if you remember back from the example, the water here acted as a base, a proton acceptor. Here it acted as an acid. It donated its H to that ammonia to form ammonium. So is water an acid or a base? Huh. Kind of a trick question. Water can be both. Water can be both, depending on what else is in solution with it. A substance that can be both is referred to as amphoteric. It's a substance that can act either as an acid, proton donor, or as a base, a proton acceptor. Water is but one substance that can do both. Okay, so Arrhenius acids generate H+ in solution, and really the hydronium ion in solution. Bases generate hydroxide ions in solution. Bronsted-Lowry acids, a little broader definition, proton donor. A Bronsted-Lowry base is a proton acceptor. And that is the end of this screencast.